Hi everybody, today we're talking about multiple linear regression in Python. And more importantly, we're going to use the statsmodels.api to define our model and to estimate our model and get some output from that estimation. So what is actually multiple linear regression? Well, in a previous video, we have gone through the simple linear regression model. In this simple linear regression model, we have a variable that we want to explain or predict, and we use one other variable or information from one other variable, in this case x, to explain the variation in the y variable. So if we are given a value of the x variable, then we can use our estimated model to make a prediction of the y variable. So for example, if we want to explain the sales, like unit sold, for example, and we would like to estimate that by use of the price, then if we get a price of a product, then we can estimate how many products or units we are going to sell. But this will be with an error, so we have an error term here. But with the multiple linear regression model, we use information from several explanatory variables to explain the dependent variable. And if we gather all these x vectors here into one matrix, then we get this term here. So, without further ado, let's get to it. So we are going to use the miles per gallon dataset for this video. And in this dataset, we have seen that there are some, not a number, values for horsepower. So we just remove those, in place equals true, then we are actually changing the MPG data frame itself. And then we are going to look at what we have. So we are looking at the 5 first rows. But of course, we have to import both pandas to make use of the data frame. We are going to use NumPy to make some random numbers later on. We use matplotlib.pyplot to plot our data, and we use the statsmodels.api to define and estimate our models. So now we can read the mpg.csv file. We drop any not a numbers, and we are looking at the dataset. And here we see that we have miles per gallon, we have cylinders, horsepower, weight, acceleration, model year, origin, and name. But from this, we are going to pick only 2 variables to explain the miles per gallon. So we would like to use information from more than one of these other numeric variables in order to explain this miles per gallon. So in this case, we're going to go with horsepower and weight. And both of these are numeric variables, so we can run a correlation. We can run the correlation matrix, and we see that, well, the correlation between miles per gallon and itself is +1 because they are the same variable. But the correlation between miles per gallon and horsepower is -0.77, and the correlation between miles per gallon and weight is negative 0.83. So this is good because a correlation of 0 would be quite bad for us. But we also see that the correlation between horsepower and weight is 0.86, which means that they are quite closely related in a linear sense. So this might induce some multicollinearity in our model, but that's a topic for your econometrics class. But this high correlation would mean that the betas, the slopes here, they would be unbiased, but they would have a large standard error. So the uncertainty of our betas would be quite large. So if you have a lot of columns, then you can use the dot columns method, or attribute, I should say, to just get a list of the column names. So here we have 5 potential explanatory factors, which are cylinders, horsepower, weight, acceleration, and model year. But we just include 2 of them. So from the miles per gallon data frame, we choose 2 columns, the horsepower and weight, and we set these as the explanatory variables. And remember that you have to pass these in as a list. So here you have a double square bracket around the horsepower and weight columns. Whereas the y variable is only 1 column. It's the MPG, so you do not have to put MPG into a separate list. So if we run this, then we have x equals MPG. So if we just write, for example, x head, then we see that we have horsepower and weight in our x variable, or our x data frame. But in order to have the constant term, this alpha is the constant term in our model, then we have to add a constant, which is 1. So we can use the statsmodels dot add constant method or function, and we pass in x. So this add constant would add a column of ones to our data frame, and then we save this data frame as our original data frame. And what we also do is that we use this data frame in the OLS function. So this OLS function, it defines the model that we are going to use. It should be a ordinary least squares model, which is a linear model, and we have a y variable, and we have several x variables. So if we, for example, if we just do this, we add the constant, and then we can check the x variable and see what we got. So here we have a constant term, we have horsepower, and we have weight. So the constant term will be our alpha, or will be multiplied with our alpha. Horsepower will be multiplied with our beta 1, and weight will be multiplied with our beta 2. So that's how we fit our model. So with this defined model from the OLS, and we pass in the data frames, we use the fit method of this object, of this model object, and we put the result in a regression result object. And this regression result object has, among other methods, it has a sorry, it has a method called summary, which prints out our regression results. So if we run this, we see that, well, we have an R squared of 0.706. We have the adjusted R squared of 0.705. And we have, more importantly, the F statistic here, which says that it's highly unlikely that our slopes, the betas on horsepower and weight, are jointly equal to 0. So we know that, well, at least one of the coefficients on the horsepower and weight should be different from 0. If this F statistic had been above 0.05, for example, then we would not have rejected the null hypothesis of these being jointly equal to 0, which means that we are better off, or we might as well just use the constant term as our guess for the, or prediction for the miles per gallon, no matter what horsepower and weight the car has. But we are actually rejecting our null hypothesis here because we have a very, very low p-value for the F statistic, which means that we should use the information in horsepower and weight when we make some predictions about the miles per gallon for a specific car. So our coefficients here, we have a constant, which is our prediction of miles per gallon if horsepower and weight is equal to 0. Well, a car with 0 weight and 0 horsepower is nonsense. So this is what we call an extrapolation, which means that it has only a value for prediction of the MPG together with horsepower and weight. So this is the main parts of the regression output. If you want a more simple if you want a more simple output, then you can use the print function and you get this kind of output. So how do you actually get a hold of these coefficients? Well, these coefficients are parameters, and in the regression result object, you have an attribute called params for parameters, and this contains all the values of the coefficients. So if you want the coefficient for the constant, you can just write the name of the coefficient after params. So the regress params constant, we can put that value into a variable called alpha and use this in a print statement, for example. This constant has a lot of digits, which means that we can use the round function to round the value 45.6402 and so on, which is stored in alpha, to 2 digits. And we have to typecast it to string to be able to print this. So we just run it and we print the constant term for the regression line is 45.64 miles per gallon. And we can do the same for horsepower and weight. So here we do the exact same thing, and but here the numbers are quite small, so we want 3 digits instead of just 2. So we just write regression result.params, and we want the horsepower. And we can use this in a print statement because as we have stored the value in beta1, we just use the variable, the contents of the variable beta1 here in the print statement. And just to conclude, we can do the same for the weight parameter, or the coefficient on weight. So we predict that 1 additional pound to the weight of the car changes the miles per gallon by negative 0.006, which means that heavier cars can go a shorter distance per gallon of gasoline. We can also get a number of different other variables or numbers from our regression result. So for example, we had the adjusted R squared, which is 0.705, and if we want to get a hold of that, we can just write regression result dot, and this has an attribute R squared underscore adjusted. We put this into a variable R squared, and we print horsepower and weight explain 100 times this percent of the variation in miles per gallon. But here we can use the R squared instead, because the R squared adjusted does not have this interpretation. The R squared does, but when we do multiple linear regression and we want to compare different models, for example, we would like to compare this model with horsepower and weight to a model with horsepower, weight, and the number of cylinders, for example. We could then use the adjusted R squared to compare different models, because the larger, or the adjusted R squared, is really the R squared penalized for the number of variables in the model. So if you throw in one extra variable here to explain miles per gallon, then you could check the adjusted R squared. If this increases, then you know that the included variable, the extra variable, is explaining a significant part of the variation, an extra significant part of the variation in miles per gallon. But if you add just a random variable, which is not correlated with miles per gallon, then adjusted R squared will actually go down. So R squared is how many, or the proportion of the variance in MPG, which is explained by our two explanatory variables, whereas the adjusted R squared is the R squared adjusted for the number of variables we have used. So this is just the adjusted R squared is used for comparing different models. So we often use this adjusted R squared. So we see that horsepower and weight explain 70.6% of the variation in miles per gallon. So here we have an estimated regression line, where the regression line is given by this equation here. So if we now set alpha equals to the constant, beta 1 equals to the beta 1 on horsepower, or the slope on horsepower, beta 2 equals the coefficient on weight. Now we can use this model to predict the miles per gallon for a car where we have the horsepower and the weight, but not the miles per gallon. So now we can actually use the horsepower and weight, and we can predict the miles per gallon for a specific car. So what if we put the maximum weight and the maximum horsepower in our data set, and we predict the miles per gallon such a car would go? So how many miles would this car go in on 1 gallon of gasoline? Then we can use the predict method from the reg result object, and we have to pass in some data, because we have to pass in 1 for the constant, because this is going to be multiplied with the constant here. We have to pass in the horsepower of the car, which is going to be multiplied with the slope for horsepower. And we have to pass in weight, which should be multiplied with the slope on weight. So if we run this, then we see that, well, such a car would go 4.9 miles on 1 gallon, which means it would go quite short. But what if we choose the smallest weight in our data and the smallest horsepower in our data? So this would be a light car with very few horsepower, so the engine would be very small. And we do the same, we use the predict method of the regression results object, and we pass in the constant, the horsepower, and the weight for this car. And this car would go a lot longer. So this would go about 34 miles on 1 gallon of gasoline. So if you're interested in saving the environment, then you would, and you do not need anything else than a light car with a small engine, then you would get 34 miles on 1 gallon of gasoline. This is just an estimate, so there is an error in this. So this is just saying that such a car would, according to our model, go 34 miles on 1 gallon on average. So if we pick several such cars, the average they would get would be 34 miles. Some would go further, others would go shorter. So, but what if we want to get the prediction into our data frame? So if we see our data frame again, we take a look here. We have miles per gallon, cylinders, and so on. But we want our model estimated miles per gallon, our fitted values, to be here in our data frame. So what we do is that we pass in all the x variables, which is the constant term, the ones, and the horsepowers, and the observed weights. And then we get a prediction for all the observed values of our x variables according to our model. And we put this into this prediction object, and this just contains one column, and we set a new column. We generate a new column called predicted miles per gallon, and we set the values in this column equal to the predicted values. So let's see what the top 5 observations would be. So according to our model, we have the horsepower and the weight times our slopes and add on the constant term, then we get the predicted value. And we see that the predicted value is different from the observed value. And this is because we have a residual. So if we take the observed miles per gallon minus the predicted miles per gallon for such a car with 130 horsepower and 3,504 pounds of weight, then we get a negative residual of over 1. So, but all these residuals, they sum up to 0. So we can take the sum of the miles per gallons and the predicted miles per gallons, and we should see that, bar some rounding error, this is basically 0. The problem now is visualizing the regression line. So how do we visualize these points? And in simple linear regression, we could just have the value of the x variable on the x-axis and the predicted values on the y-axis, and they would fit on a straight line. But here we have both horsepower and we have weight, which means that we have one more dimension. And this means that if we are using horsepower and weight, and we plot these with the prediction, we actually get a plane. And this is not a line, but it's like a sheet of paper, which contains the predicted values for any combination of horsepower and weight. But it's difficult to actually plot this. So what we usually do is that we can plot several kinds of plots. One is the regression line between the dependent variable and one of the independent variables. And the other is actually the predictions of y against the actual y's. Because these should have a linear relationship and the variance should be constant no matter which level of y or prediction of y we are looking at. So first we want to make a scatter plot of predicted miles per gallon and the observed horsepower. And this does not produce a straight line as previous, because we have problems with that each of these observations, these fitted observations, they contain a different weight. So what we can do, we can set the weight for all these observations equal to the average weight, and then we could plot the estimated horsepowers, estimated miles per gallon given a certain horsepower of the car. So here we make a copy of our x variable. It's called x2, so it contains so we can just do this. We can take x2 dot head, and let's see, we just do that here, and then we can do this. Okay, so first the x2 looks just like the ordinary x data frame. It has a constant, it has a horsepower which differs between the cars, and it has a weight which also differs between the cars. But what we do is that we set one variable equal to the average, then we plot the y variable versus the leftover x variable. So if you want to plot in a multiple regression, you want to plot one variable, one x variable versus the y variable, then you set all the other x variables equal to their average. And we can do that by doing this. We do not need to calculate a separate variable. We can just do this. So the weight column should be the average, the mean. So the mean and average mean the same of the weight column. So what does this look like? Well, now the weight column is just the average weight of the cars in our sample. So now we can make some new predictions with this data set. So we just predict based on our regression result. We predict a new miles per gallon. So here we can just put this in a variable. Well, we do not need to, but as we showed here. But what we do is that we set this predictions, or these predictions we set into a new column called predicted miles per gallon with mean weight. So then we have yet another prediction, and this is for all cars given a mean weight, but different horsepowers. So then we can just plot this horsepower on predicted miles per gallon for the mean weights. We would also like to see the actual observed values, and we do that with a scatter plot of miles per gallon on horsepower. We label these as actual miles per gallon, and we label our estimated points as the regression line. And then of course we set a title, a label on the Y and X axis. And we also add the legend to make these labels show in our plot. So here we can we actually get an error message here. Let's see, weight mean is not defined. Oh yeah, because we have up here I've removed the weight mean variable. So if we had run this, we had put this into a variable, and of course if you want to use the information you get from this on the later stage, you should put it in a variable. So now we can run this again, and we get for a weight of 2,977 pounds per car, we get a new regression line here, and this contains the information in horsepower adjusted for the weight. So here we can plot the Y variable versus the predicted Y variable. And what we also want to plot is a line of the Y variable versus the Y variable. And we have labels, and what we have here is that if this model was perfect, then this predicted miles per gallon would lie on this line here, and it would be equal to the actual miles per gallon. So this line here is going 45 degrees up here because it's the actual miles per gallon on the actual miles per gallon. Whereas the dots here, they are the miles per actual miles per gallon on the predicted miles per gallon. So here for cars with a low miles per gallon, the predicted value is actually lower than the actual miles per gallon for that car. For cars with a medium miles per gallon value, then our model is predicting a too high miles per gallon. And for cars with extremely high miles per gallon, then our model is predicting too low miles per gallon. So ideally, our predicted, these dots, they should lie on this line or be scattered around this line, I should say. We have talked a bit about the R-squared versus the adjusted R-squared. And the R-squared is increasing when we add more explanatory variables. Even if the explanatory variable is not explaining a significant part of the variation. And the adjusted R-squared penalizes the number of explanatory variables and does not increase if the explanatory variable has a low correlation with the dependent variable. So if we set a seed here from the NumPy package, we use the random sub package or subfolder, and we have a method called seed, which is defining our starting point for the random number generator or quasi-random number generator. So you have to set the seed to get the same random numbers, in quotes, as I do here. So here we are going to make a set of random numbers with a length equal to the observations in our MPG dataset. So we are making 3 different series of random numbers. So here we have some integers, random integers up to, well, from 0 to 99, to and including 99, not 100. And we have a random, a series of random numbers here as well. So if we generate these, then we see that, well, we have generated 3 columns here in our MPG data frame, and we set each of these equal to the generated random generated series of random numbers. So here we have random 1 and random 2, they are integers, and random 3, it's a decimal number between 0 and 1. And by chance, some of these random numbers or series of random numbers might correlate with our MPG variable. And we see that, well, random 1 does not correlate with MPG. However, at random, the random 2 series has a positive or a slight positive correlation with the MPG variable. Whereas the random 3 does not have a large positive variation or covariation with the MPG variable. So if we add these to our explanatory variables, then if we just run the ordinary regression again, with our two explanatory variables, horsepower and weight, then we see that, well, we had an R squared of 0.706 and we have an adjusted R squared of 0.705. But if we add random 1, random 2, and random 3 to our regression, then of course we have to remember to add our constant. Then we fit our model and we run the regression summary. Then we see that just by adding these series of random numbers, our R squared has actually increased to 0.709 from 0.706. But our R squared did not bulge. So the R squared told us that there is no extra information in these random numbers. So we should just keep our original explanatory variables in our model and not include the random numbers.